Hello, class. In these series of models, we're now going to switch gears and we're going to talk about the quantum mechanical model of the atom. Let's refresh our memory a little bit and go back to a model you may have learned in introductory chem. So there's three models. The first model is Rutherford's model that we're going to speak about. So in this model, you guys learned that in the center of an atom, in the nucleus, you have some protons and you have some neutrons. And there's a region occupied by the electrons out here, a region of space. And this was mostly empty space. And in this empty space, we have electrons. And there are as many negatively charged particles or electrons as positively charged protons that are inside the nucleus. So your numbers of your electrons and your protons are going to be equal, and that leads to an electrically neutral atom. So that's our Rutherford model. We've already went over the Bohr model in a previous module, but I wanted to go back just to refresh our memory a little bit since we're talking about models. And here it was based on the hydrogen atom. So again, you have rings around the nucleus. They're called orbits. Electrons move in these orbits around the nucleus. These orbits are quantized. They have fixed values. And our electrons, they are not allowed to go in between the orbits. So electrons can move in a couple different ways. So if we go look at our orbits, it's n equals 1, 2, 3, 4. So if you go from a lower energy orbit to a higher energy orbit, to a higher energy orbit, that's called excitation. So you need energy to do that. So energy is absorbed. And when you go from a higher energy orbit to a lower energy orbit, that's called relaxation, and you emit light, and it's emitted as a photon. So we talked about that, and that is our formula for the photon emission. So that's the Rutherford model and the Bohr model. Now we're going to go towards the quantum mechanical model. So now the quantum mechanical model, we're going to review a few things first. So like we saw with velocity and position, the same is going to be true about energy and position for our quantum mechanical model. Those are complementary for an electron. The more we know about its energy, the less we know about its position. Okay. Well, how do we get the energy? So the energy of the electron, we calculate those using wave functions. So these come from solving the Schrödinger equation. So these wave functions come from solving the Schrödinger equation. So what is the wave function? Well, our wave functions, we use the symbol psi, and it's a mathematical function that describes the wave nature of an electron. And a plot of psi squared, this represents an orbital. And its position or probability distribution map of our electrons. So we're going to be going over what these plots look like. So we also have that dots will represent probability of finding the electron. Again, we're going to go over it more, but we can describe the probability distribution of where an electron will be by plotting dots. So we're going to go over what's called a dot plot. And again, sorry about that, we specify the energy of our electron precisely. I don't know why my pen's not working today, but not its location. But not its location. So we're going to look at the results that come from solving the Schrödinger equation for our hydrogen atom. So when we solve the Schrödinger equation, this is going to describe the behavior and properties of our electrons. So Schrödinger, he took some of those ideas we talked about before, took the new ideas from the time, and came up with quantum mechanics. So when you solve the Schrödinger equation, what do we get? So the first thing to take note is when we solve that equation, you get quantized energy. We've talked about that before. And recall, this is where you can only have fixed energies. This is like, another analogy I like to use is this, these are like channels on a television. There can only be one channel at a time. You can't, watch it in between channels. Another thing we can get from solving the Schrödinger equation is our wave function. So I just mentioned the wave function earlier in this module, and we know that the symbol is psi, but there's some things that we need to point out about the wave function. Now, when we solve for this, we need to solve for a particular wave function. And here we're going to look at different orbitals. So we have some quantum numbers. Now, we're going to go into detail about what these numbers are, but first let me start to explain it here. So this is supposed to be an n. So we'll have psi n, and then we're going to have L, and I'll explain what these are in a moment, and then we're going to have m sub L. So to keep track of everything, we need to use these symbols. Now n, this is called the principal quantum number. This is the principal quantum number. L, this is another quantum number which is called angular momentum. Angular momentum. And then m sub L is called the magnetic quantum number. This is our magnetic quantum number. So over here, n, those are going to be integers like 1, 2, and 3. So we've seen those before. And L, these are going to be represented by a series of numbers. We start from 0 and we continue till we get to n minus 1. And then m sub L, we start at our minus L. We go through 0 till we get to a positive L. Okay. And this will make more sense in the future as well, but I want to just start to talk about it here. So this describes a particular wave function. So what do the wave functions tell us? Well, if we take our wave function and we square it, so if we take our wave function and we square it, this tells us, this gives us the probability of finding an electron. Okay, that's our probability of finding our electron. Now, how could we look at the psi squared? Well, again, recall that psi, again, our wave function is just a mathematical equation. So what we're going to do is we're going to look at 4 different kinds of plots, all again for hydrogen. So that's how we're going to determine the probability of finding our electron. Okay, so what are these plots? So we're going to look at what's called a radial plot. That's the first type of plot. And a radial plot is if you have a proton, and we know the electron is somewhere out here, we're going to draw a distance r. So that's our radial distance from the center of our nuclei of the atom. And we want to know where this electron is likely to be located. So what we'll do then is we'll take our plot here, and this is our probability. Here, our y squared. And here on the x-axis is our R. So when R equals 0, we know that there's going to be 0 probability of finding the electron here, because this is going to be right on top of the nucleus here. So that starts at 0. We want to see what things look like as we get further out here. So further and further from the nucleus. So what is the probability of finding the electron some distance here from the nucleus? So we're going to look at plots like this. The second type of plot, and I mentioned earlier, is called a dot plot. Now, with the dot plot, we see these little dots, and the density of dots, they will say something. So if you guys can see the dots, where is it more dense? Here, we have a higher density in the center, and then we have a much lower density out here as we're going away from the center. So here, we have a lower density. So we know that in the center then, this is where we would most likely find our electron. Those are dot plots. And then the third type of plot we will be going over, they're called radial probability distribution plots. Radial probability. I don't know why my pen is not working. Distribution plots. Sorry guys, I'm going to try to clean my screen after this. Okay, so we're going to go over that in detail and then in the next module. And the final plot is called a contour plot. And again, we're going to go over what the contour plot looks like in the future module. But what I wanted to go over first is for the hydrogen atom, we want to look at what the different wave functions look like. So we're going to start with the smallest numbers. So we are going to start with the psi of the smallest quantum numbers, n equals 1, L equals 0, and m sub L equals 0. So notice here there's just a lot of numbers, 1, 0, 0. So what chemists did, they kind of came up with a code for our angular momentum L. So L, we know that there are going to be numbers like 0, 1, 2, and 3. But chemists decided that instead of just having a lot of numbers, we are going to use letters. So 0 would be S, 1 would be P, 2 would be D, and 3 would be F. Now, theoretically, we're not going to see it, but theoretically, you can have a 4, so that would be G. But these are the ones that we focus on, and a lot of you have already learned these when we learned about electron configuration. Remember when you did the 1s2, 2s2, and so on? So here is where it comes from. So we are going to substitute in the numbers here instead of saying 0. How we would write this then for the smallest quantum numbers, we would write a psi of 1s, just like we did with electron configuration back in the day. So here the smallest or the ground state would be the 1s. So our n equals the 1. And the S comes from the L here. Our L equals 0. So we're going to see this notation a lot, so I just wanted to make sure that we went over this before we look at the different kinds of plots. Okay, so that's the end of this module. The next module, we will be looking at the 4 plots that I just went over.